enlightened geometry students. In this assignment, we are going to introduce you to similarity. Similarity, or two things being similar, means that they are the same shape but different sizes. So for example, here in the foreground, we got a little car, and in the background, you got a full-size car. They're the same shape but a different size. We say that these two objects are similar. In fact, any little scale model of something would be considered similar to the full-size object. It's the exact same shape and proportional, but just different full sizes. You might be used to this with the globe in your classroom is similar to the full size of Earth. Or in the problems that we did just the other day, we have the Hot Wheels track you had when you were a little kid and building the loop might be similar to the full size one that was built in Las Vegas. Okay, so starting with similarity and identifying when things are similar. Let's say you have a picture of your favorite cartoon character and you take it over to a copy machine and make a whole bunch of copies of them. And this is what the machine spits out after you press a whole bunch of random buttons. Now, the first question you want to ask is, which one is an exact copy? Which one is congruent? Congruent is what we talked about first semester when things are the same size and same shape. So which of these pictures represents one that's congruent to the original? That's right, it's letter E. This one hasn't changed. So what we want to look at is what's wrong with all the other ones. See, the first one, letter A, this one has been shrunk down. It's smaller than the original. And problem B, the legs have been cut off. If you're a photography person, you know that that is called cropped. And problem C, the picture has been stretched or skewed. Problem D, or picture D, we have an enlargement of the picture. It's the same picture, but bigger. And problem E is the exact same. There's been no change. So again, we talked about things that had no change. They were exact copies first semester. Now we're going to talk about these two. When we take some object and shrink it or enlarge it. It should sound a lot like dilations. Remember dilations from first semester, where we take an object and we make a larger or smaller copy of it. Dilation is like the verb. That's what you're doing to the shape. But we say that the two shapes are similar. They're the same shape, just different sizes. We talked about dilations with a whole bunch of things. You take a small thing and make it big, or take a big thing and make it small. We don't need to go through that. But the end result is we end up with two objects or two shapes that are the same shape, but different sizes. We did this a whole bunch of different ways first semester. So what are we going to do with our similar objects? Well, the thing that's going to be different, other than simply identifying them, is finding measurements. For example, here we have two similar triangles. They are the same shape, just different sizes. We have some of the measurements in this little one, and I'm going to give you one of the measurements in the big one here. So in this side, say we know that this side here is 6 inches. If you compare that to the original triangle, which side is it in the corresponding location with? See, the 6 inches in the big triangle corresponds to what measurement in the small triangle? Well, it goes with the 2. See, this 2 inches on the left side gets multiplied by 3 to become the 6 inches on the left side in the big triangle. It's always multiplied. We're not talking about adding 4. When we talk about similar objects, we're always multiplying by something. Now, this multiplying by 3, 2 times 3 to get 6 for the missing side, we can use that once we know this special magic number that we're multiplying by, we can use that for any of the sides. For example, if I want to find the bottom of the big triangle over here, I'm just going to do the same thing to the corresponding measurement in the little triangle. So if I want to know how big this bottom is, I'm going to take the corresponding measurement in the little triangle and multiply that by 3. What's the length of the bottom in the big triangle? It's 15. We just do 5 times 3 to get that. Now, a couple of important things here. We'll go into more detail on later. But this number that we're multiplying by, we multiply by 3, and we could multiply all the measurements by 3 to get this. That thing that we multiply by is called the scale factor. You're going to hear that phrase a lot in the next few days of class. Scale factor. It's what we multiply similar objects by, the measurements in one similar object by, to get the corresponding measurements in the other similar object. Now, in this case, we say we're multiplying the little one times 3. We could also do this backwards. We could take the big one, and I know most people would think of, oh, I just divide by 3. 15 divided by 3 gives me 5, or 6 divided by 3 gives us 2. But we want to think of it in terms of multiplying. That's because later in math there are some formulas, and we want to keep our scale factor as multiplying. Otherwise, we have to have two formulas. A formula with multiplication when we're getting bigger, or a formula with division when we're getting smaller. We can keep everything down to one formula if we think of our scale factor as 1/3 when we're getting smaller, or 3/1, or just plain 3 when it's getting larger. All right, this is a symbol that everybody here is familiar with. This is an equal sign. You've seen this since you were in 1st or 2nd grade. If two things are equal, it means they're the same size. They have the same value. We've seen this symbol. the little squiggly line called the tilde. It's on your keyboard in the upper left-hand corner. We use that symbol in mathematics to represent things of the same shape. You've seen that before because we've already talked about things being congruent, both the same size and same shape. The equal part being same size, and the squiggly little line part being about being the same shape. But in this case, for this unit, we're just going to be talking about things that are the same shape. So we will use this symbol, the tilde, to represent that. For example, here are two triangles that are the same shape. These are similar triangles. How would I represent that? Well, I could write out these are similar triangles, or I could use that little tilde sign to represent it. Big triangle, similar to little triangle. And what we're going to try to do in a problem like this is figure out this missing measurement, the x here. So this is what we want to do, is find this x. Now to find x, undoubtedly, some of you guys are already coming up with a shortcut to do this, or your own way to do it. There are lots of ways to do these problems, and a lot of you will come up with your own ways to do them. However, whatever little shortcuts you might find that work for one problem may not work for another problem. So what we're going to focus on in this video is a method that works for every problem. But yes, there are several different ways you can do the problem. But the one thing that always works is to take your information and organize it. We're going to basically create a little chart. Every time we're doing one of these problems, the information can be broken down this way. We have two objects, a big object and a little object. And we have two measurements. And it doesn't matter what we call the measurement 1 and measurement 2 is what we have here. But basically, big object, little object. And what we want to call measurement 1 or measurement 2 doesn't matter as long as we get the same measurement from both triangles. For example, for measurement 1, I'm going to use these two sides, 24 and the 16. I don't have to use 24 and 16. I could use 21 and x, which I'm going to use for measurement 2. But you can't mix and match. You have to get the corresponding measurements from the triangle. If you use 24 in the big one, you have to use 16 in the little one. They have to go together. And all we're going to do is we're going to fill out this little chart and turn this into a really simple problem. In the big triangle, measurement 1, we just said was going to be 24. The matching measurement in the little triangle, the corresponding side, has a length of 16. In the big triangle, measurement 2 was 21, and the corresponding measurement in the little triangle was x. Once you have this, and you don't really have to write out the chart, but you do have to organize it into some information like this, we have our four numbers written in a grid like this, and we're just going to turn it into a proportion. A proportion is when you have two fractions that are equal to each other. Now, we're taking up a lot of room here. I'm going to shrink this up and make this picture a little bit smaller like this, and here was our proportion. 24 over 21 is equal to 16 over x. We've already talked about how to solve a problem like this. We're simply going to cross multiply to solve. 24 times x is 24x. 16 times 21, you may have to bust out a calculator, beep, boop, 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 bop, and you get 336. We set these two values equal to each other and solve for x. In this case, we're just going to divide both sides by 24, and we end up getting 14. The missing measurement in the little triangle is 14. Again, yes, there are several other ways to do it, but some of those other tricks only work in certain types of problems. This will work for every problem. Now, you may not like this method because you had trouble remembering the chart, or you didn't know why I organized it in a certain way and not another way. But that's okay, because you can organize your chart a lot of different ways and have it still work. You just have to have it organized. See, cross-multiplying it this way gets us to 14. But if, say, we had the fractions reversed, 16 over x equals 24 over 21. When we cross-multiply this, we get the same equation and the same value for x. We could even have organized our chart another way and ended up with this, and have 24 over 16 equals 21 over x. When you cross-multiply, you get the same equation and the same value for x. There are several different ways you can organize this. In fact, you can take these same words to describe the chart and rearrange them in a handful of different ways. It doesn't matter if you put the big on top or the little on top, the big on the left or the little on the left, measurement 1 on top or measurement 2 on top, or put the measurements going across and the different shapes going up and down. You can do this a couple different ways, as long as you get that information organized. So one of the key things to do in these problems is being able to cross-multiply properly. So let's take a minute and try this. Here are three problems. Cross-multiply and solve for x. And in the first problem, we get x is 2. In the second one, x is 16. And in the last one, x is equal to 25. Now, there's harder versions of cross-multiplying problems like this one, but we've seen this before, hopefully. When we cross multiply here, we're still going to follow the same steps. 1 times 10 is 10. But when we do x plus 4 times 2, we have to distribute the 2. It's really 2 times x plus 4 in parentheses like this. So we must distribute the 2 and make that 2x plus 8. All we did differently is when we did x plus 4 times 2, the 2 had to be distributed. Once you've done that, the rest of the problem is a pretty straightforward Algebra 1 problem. We're just going to subtract 8 from both sides and then divide by 2, and in this case, we're going to get x is equal to 1. Take a moment, try problem number 6. All right, for problem number 6, we're going to cross multiply. 3 times 20 is going to give us 60. X minus 1 times 4 is ultimately going to give us 4x minus 4. Solve it just like an Algebra 1 problem. Add 4 to both sides, divide by 4, and we're going to end up with x is equal to 16. If you haven't done it yet, do number 7. In number 7, same first steps. We're going to cross multiply. 6 times 21 is 126. 7 times x plus 2 will ultimately be 7x plus 14. So we subtract 14 from both sides, divide both sides by 7, and we're going to end up oddly with the same answer. X is equal to 16. The problems can be a little trickier like the one you see now. The triangles, not only do we have a dilation that's happened, but also a rotation. When something like this happens, when the triangles have been spun around or reflected, step 1 is to identify which parts go together. So we have to find the corresponding measurements. For example, if we start with the 20 in the big triangle, I want to find the matching measurement in the small triangle. Use the tick marks that are added to the picture to tell. See, 20 is between the angle with 2 marks and the angle with 1 mark. So the matching measurement in the little triangle is going to be the 5. It's in the same place with respect to the angles. Likewise, the 16 down here is in the same place as the x. So those are our corresponding measurements. Once you know that, the rest of the problem is done the same way. You organize your information, perhaps a chart like this, fill in the numbers into the chart, and then simply cross multiply to solve. In this case, 20 over 16 equals 5 over x. Cross multiply and solve this one, and we're going to end up getting x is equal to 4.